In the last section, or in the beginning of this section, we started talking about universal and existential quantifiers. These are symbols we use to express that for all x values, some open sentence is true, or that there exists an x value that makes a particular sentence true. So for example, if we looked at this statement here, there exists an x such that x squared plus 1 is equal to 0. We haven't specified a system here, so we can assume x is a real number. So this is asserting that there exists a real number x such that x squared plus 1 is equal to 0. Is this true or is this false? Well, we've seen that to show that this is true, we would need to find a particular x value that makes x squared plus 1 equal to 0. In other words, we need an x value such that x squared is equal to negative 1. Rewriting that equation gives us x squared is equal to negative 1. But that's not true, because we've also proved in another one of these exercises in the last video that x squared is always going to be greater than or equal to 0. So it can't be equal to negative 1. So this is going to be false, because there is no real number x such that x squared is equal to negative 1. We proved that x squared is greater than or equal to 0 for every real number x. Okay, so this is a false statement. But remember, if a statement of some form P is false, we know that its negation is also true, which means the negation of this statement has to be a true statement, because this statement itself is false. So what is the negation of there exists an x such that x squared plus 1 equals 0? Well, to say that this is not true means to say for every potential x value, so for every x in R, it's not the case that x squared plus 1 is equal to 0. Which we could write this as a universal statement now, right? Because this is a for every or for all statement. So we could rewrite this as for every x, we can leave out the in R because we assume it's a real number if we don't specify. So for every real number x, x squared plus 1 is not equal to 0. Alright, now notice that when we negated that existential statement, the quantifier changed from exists to for all, from there exists to for all. And also the condition or the predicate, the stuff that comes inside the parentheses, also got negated. Right? So exists x became for all x, and then the predicate part, x squared plus 1 equals 0, got negated to be x squared plus 1 is not equal to 0. Alright? So we can say in general that the negation of the statement there exists an x such that p of x is going to be logically equivalent to saying for all x it is not the case that p of x is true. Right? And analogously, the negation of a universal sentence should result in an existential sentence. So to see why that is, let's consider the statement for all x, for every x value, x squared is greater than x. I claim that this is a false universal statement. Why is this false? Well, it's not true that every x value satisfies that x squared is greater than x. I can give you a counterexample. So, as a counterexample, let x be equal to 0. Then it's not true that x squared is greater than x. X squared is not greater than x. 0 is not greater than 0. Right? We found a counterexample, which means this universal statement is false. So what is the universal statement, or what is the negation of this universal statement? To say that for all x, x squared is greater than x is false means to say that there is at least one x, there is an x value, such that our predicate, x squared is greater than x, is false. In other words, x squared is not greater than x. This is sort of a silly symbol. We'll come back to that in a minute. But keep in mind that this is an existential statement. There is an x. There exists an x. There exists an x, such that x squared is not greater than x. This is the negation of this original statement up here, x squared is greater than x. Except, okay, realistically, we don't really write not greater than in this way. If x squared is not greater than x, what that means is x squared has to be less than or equal to x. This is how we would normally write a negation of a greater than symbol. We just use a less than or equal to symbol. So notice when we negate a for all statement, a universal statement, we get an existential statement. So we can say that the negation of for all x p of x would be there exists an x such that not p of x. So let's do one more example together. We're going to write the statement x cubed minus 3 is prime for some integer x, and we're going to write its negation in symbols. All right, first let's write this sentence symbolically. Is this universal or is this existential? Well, it says for some integer x. So this is just asserting that there is at least one integer x that makes this true. That means your original sentence is going to be an existential sentence. There exists an x such that x cubed minus 3 is prime. Okay, I have to use words in here because we don't have symbols yet for prime. Okay, now the negation, according to what we've seen in previous pages, the way that we would negate an existential quantifier is we negate an existential becomes a for all, a universal. So this would be for all x. And then the predicate, the stuff inside the parentheses, gets negated as well. So to say x cubed minus 3 is prime, to negate that would be to say x cubed minus 3 is not prime. So the negation would say for every integer x, I should have been more careful here. This is stating for some integer. So I need to make sure when I'm writing my quantifiers out here, I'm specifying there exists an integer x, or there exists an x in the set of integers. Similarly for all x in the set of integers. Okay, should have been more careful there. Now, which one of these is true? I don't know off the top of my head. In general, it's easier to prove existential statements are true than it is to prove that universal statements are true. So I'm just going to go ahead and start looking for a witness for my original statement. And if I can't find one, then I can go ahead and look at the universal statement and see if that's true instead. So I'm just going to start choosing some x values to see if this works. If I tried x equals 1 as my witness, it's not true that 1 cubed minus 3 is prime. This gives you -2. Negative numbers are not prime. So this doesn't work as a witness. Okay, but that doesn't mean that there isn't a witness, it just means 1's not the witness. So let's try another witness, potential witness. So when x equals 2, we'd have 2 cubed minus 3 would be 8 minus 3 would be 5. Aha, 5 is prime. So that means that my original statement has to be true because it's an existential statement and we found a witness. So x equals 2 is a witness that the original statement is true. And that means that the negation would have to be false because an original statement and its negation always have opposite truth values. So in the next section, our last section on Chapter 1, we'll talk about combining quantifiers. So using more than one quantifier in a single statement.